Hello, welcome everyone to recitation number 8. The topics today, two different topics, related rates and linear approximation. My goal is to have 6 problems, 3 of each. Actually, maybe 2 and 4, I don't remember. But related rates problems are usually longer. So we're going to start with those. Here is a related rates problem. We know it because it's basically a word problem. So in this problem, a square initially has side lengths of both 100 meters, but it's actually changing. It's getting both taller and thinner. The height is increasing at a constant rate of 3 meters per second, but the base is decreasing at a rate of 2 meters per second. Let's say, for example, the origin here is fixed, which means then that the x coordinates are getting smaller, but the y coordinates are getting larger. This is what's happening to this square. How fast is the area changing after 30 seconds? So the question is a prime of 30. They ask how fast something is changing. That means the derivative. And if you're thinking of this area, big A, as a function of time, then you want to know a prime at the time 30 seconds. Well, we don't have to worry about converting units. Everything is meters and seconds in this problem. But what do we do now? Okay, so we have to identify things which are changing, not just the area. The other two variables in this problem that are changing can be called x and y, the base and the height, where I guess you're measuring them in the usual directions that you do for x and y values. So first of all, you need to find the relationship between all the variables in the problem. And this is the relationship. Area is x times y. This one could not be simpler. That's the area of a rectangle. So this relationship, once you find it, you try to find its derivative with respect to time before you start plugging in any values, anything that you know for them. Each one of these guys here is a function of t, a function of time. So when we find d dt, the derivative with respect to t, on the left, that's just dA dt, or a prime, which is the same thing. But on the right side, that's a product rule computation. X times y, both are functions of t. So you can write that like this, dx dt times y plus x times dy dt. So I'm using a slightly different notation from what I usually do for these problems. You can also do it the other way, which would be like you write the parenthesis t here for each one of these functions, and you use the prime notation for the derivatives. That's also fine. But anyway, let's keep it this way. So this is the equation that's going to allow you to find dA dt, which is what you want. You also know dy dt and dx dt, by the way, because the problem said the height is increasing at a constant rate of 3 and the base is decreasing at a constant rate of 2. So we can go ahead and plug those in here. Dx dt is actually minus 2 because it's decreasing, and dy dt is plus 3. The only thing that's missing from here is we don't know yet the values of x and y at those instants. This equation, rewriting this in slightly different notation, what it means is that a prime of any instant is equal to minus 2 times the y at that instant plus 3 times the x at that instant. But we still don't know these guys. They are certainly not 100. If you go back in the problem, 100 meters is where both x and y started. Here they are. But we are now talking about this instant at 30 seconds. So there will be different values for x and y that you can basically think about or calculate them with simple formulas. So that's going to be my next step here. What is x of t? Well, x started the initial value as 100, and then every second it decreases by 2 meters. So this is how you find x of t. It's a very simple linear relationship. Initial value plus rate of change, which is a negative number, times the time. This is all because it's a constant rate, which is usually the case in these problems. Similarly for y, it also started out as 100, but then it's increasing at a rate of 3. So these will allow you to say everything that you need. X of 30, the instant 30 seconds where we want to calculate A prime is 100 minus 60, so 40. Y of 30 is 100 plus 90. And now you're good to go. Using this formula of A prime of 30 will be minus 2 times the Y value that we just found, plus 3 times the X value that we just found. So minus 380 plus 120. That's a negative number. What is that actually? 260? This is A prime of 30. What is the unit? This is a physical problem with units, so once you find your final answer, you need to give it the correct units. Well, the unit of area, if this was just the A function without a prime, that would be meters squared. But because of you have a prime, you need to divide this by the unit of time, which is seconds. So this is how fast the area is changing at that instant. It's actually a negative derivative, so that means the area is decreasing at that instant. Which, I mean, it's not so easy to guess according to what's happening to this rectangle. One of the sides is increasing, but the other is decreasing. Which one is going to be more important? That depends on the instant. But anyway, that's it for this problem. The other problem about related rates is going to be this one. You have a drone flying through an elliptical path in air, following a certain curve, where y is going to be measuring height above the ground, and x is going to be displacement in horizontal direction in meters. So before I read everything else, I'm going to draw a picture here. That's actually not necessary for solving the problem, but we can at least visualize what's happening. If you try to draw this picture, you realize this is an ellipse because it's the sum of squares being equal to some number. It's the ellipse. I know it's an ellipse because of the different coefficients in front of these guys. There's a 4 and a 1. And also it's displaced because of this x minus 4 and this y minus 6. So it is centered at the number at the point 4, 6. So yeah, let's imagine here is 4, 6, for example. The ellipse turns out it looks like this. It's more tall than it is wide in this case. All right, so imagine this is a picture of the path of a drone flying in air, where y is the actual height and x is a horizontal displacement. So it keeps going round and round. We actually don't know which direction it goes, but it keeps following this curve. Both x and y are changing in time. Those are functions of time. All right, so I'm going to go back to the problem. Suppose that its vertical displacement speed is 2 upward when its horizontal position is 6. So this is the information that happens like at the instant where you are interested. So if you're talking about some time t or t0, let's say time t0, this does not mean the initial time. It just means a specific time in the process. At that time, we're saying that the position is 6, while the vertical displacement speed is 2. What does that even mean? Well, vertical is the y coordinate. Speed means time derivative. So we are basically saying y prime is equal to 2 upward, so positive. So this is information that's given to us at that instant. And the question is, what is the magnitude of its horizontal displacement speed? So they want to find horizontal displacement speed, so x prime at that instant. Well, not exactly x prime, but rather absolute value because they said magnitude. That's going to be important. Magnitude is the same as absolute value. But it is basically now a question of you have the two variables x and y, both are functions of t. We gave you some specific values at that instant, and you want to find some other specific value. Your first step now is write down the relationship between them, between the variables. In this case, we don't have to write it down because it is already given. X and Y are related by this equation. 4x minus 4 squared plus y minus 6 squared is equal to 25. All right, so we have the relationship between x and y. Your next step after you've done writing this down is take a time derivative. So let's do that. X and y are both functions of time. Now, for example, in each one of these terms, you're actually going to need a chain rule. Let's look at the first one here, or rather without the 4. Let's look at x minus 4 squared. If you want to find d dt of that, like call that some symbol that you want, z is equal to x minus 4 squared. You want to find dz dt, the derivative with respect to time. We're going to use this chain rule, dz du, du dt, where u is the inner function, x minus 4, and z in terms of u is u squared. This is how the chain rule works. So you see that dz du is 2 times u, but du dt, if u is x minus 4, and the variable that you're differentiating with respect to it to is the variable t, so that will be just x prime of t, or dx dt, if you will. All right, basically the du dt is the same thing as dx dt because the difference is just this minus 4 here, which is irrelevant for the derivative. And finally, replacing this u with what it means, so 2x minus 4 dx dt. This is the derivative of x minus 4 squared, just keeping in mind that x is a function of t. And then when we differentiate the equation here, we need to multiply that by this 4 here. So we're going to get 8x minus 4 dx dt. A similar thing is going to happen to the second term, y minus 6 squared. This derivative will be 2 times y minus 6 times dy dt. And the whole thing is equal to 0. The derivative of 25 is 0. Very good. So this is now the derivative. It involves the specific values of x and y, as well as their derivatives. Now at instant t0, after you've done the differentiation, you can now start plugging in the values that you already know at that instant. We were given 2 values. We were given x is equal to 6, and dy dt is equal to 2. So I'm plugging those in. 8 times x is 6, plus 2 times, we don't know y yet, dy dt was 2. So simplifying here, 6 minus 4 is 2. That's going to be a 16 in here, and there's a 4 in here. So 16 dx dt. Maybe you can write something like this, evaluated at the instant t0, just so you are sure that this is now a general equation. It's not a general equation. It's only valid at that specific instant. But then I prefer to use this notation, x prime of t0 plus 4 times y of t0 minus 6 equals 0. All right. X prime of t0 is the thing that we want to find in this problem, actually the absolute value of that. Well, we're going to need to find y first. Nobody gave us a y at that instant. They just gave us x. So we need to find this y somehow. But, well, there is a relationship between x and y. It is right here. At all instants, this is valid. So we can use that equation, the original one, to find the value of y. Let's actually do that. Using the equation was, once again, x minus, what was that? 4, and then y minus 6. This is the original equation between x and y. Using this to find y of that instant. So x of that instant is 6. They gave us a 6. So let's do this. I plugged in 6 for x. Well, 6 minus 4 is 2, square is 4, plus y minus 6 squared is equal to 25. So y minus 6 squared is 9, subtracting 25 minus 16. This means y minus 6 is actually equal to plus or minus 3, the square roots of 9. And then you're going to have two possible values for y when you add this 6 to the other side, either 9 or 3. It makes sense if you think about this, that there should be two values of y corresponding to this given value of x, because, well, going back up here, here is x equals 6, maybe another color here. If you look on the ellipse, there are two different points where it intersects the ellipse, two corresponding values of y. We don't know which one of these is our location. So that means there are possibly two answers in here. So let's just remember that this is y of t0, 9 or 6, sorry, 9 or 3. This is all that we needed to go back now to the original equation that we found after differentiating. So let me denote this special equation here by star and then continuing from star. Continue from star above, which said, once again, 16x prime plus 4y minus 6 equals 0. Now we just have the two possible scenarios to analyze. We found two values for y of t0. If it is the 9, then just solve for x prime. So 16x prime plus 4 times 9 minus 6 equals 0. So what is this going to be? This is 12. So minus 12 over 16, which you can simplify if you want by dividing by 4 minus 3 over 4. This is one possible value for x prime. There is going to be another one if y is the other possible value that we found for y was the number 3 up here. So if it is 3, then what happens? 16x prime of t0 plus 4 times, now I'm plugging in 3 up here, 3 minus 6 equals 0. You see that now this is a minus 12, which goes as a plus 12 to the other side. So in this case, the horizontal velocity would be plus 12 over 16 or plus 3 over 4. It is actually impossible to tell which one it is. We don't know. There is not enough information in the problem. As you see, you saw there were two different points where we could be. But remember, the problem was asking for the absolute value of x prime, not x prime itself. In any case, it's going to be 3 over 4. There is one answer to the problem, even though we don't know which one of the two situations we are in. By symmetry in the ellipse, you don't know if you're going back or forward. But the answer to the absolute value is clear. It's 3 over 4. I guess you should say meters per second because units were given, and this is a velocity or a speed. All right, so if you look back in the ellipse here, like if the drone is flying counterclockwise, well, then if you are in this point down here, the speed would be positive because you're going to the right at that point. But if you are at the point up there, you're going to the left. Anyway, this is what's happening here. So now let's move on. This problem, it is very similar to problems that we've done. So I'm not going to finish this entirely. Maybe this will be one of the questions that I ask in the follow-up questions in this recitation, the recitation activity. This is a very simple one where we want to find an approximation for a certain number and determine if it's smaller or larger than the actual value. So when you look at this, you have 1 over a 5th root of the number 33. You can probably guess that this is the function that you want to analyze, the 1/5 root of a number. And the number in case is the number 33. Well, it's supposed to be a difficult one to do in your head, but there should be a close number to this one where you know a value. And that would be the number 32, because 32 is a power of 2 and it is 2 to the 5. So actually the f of a, 1/5 root of 32, that's the same thing as 1/2. So that was an easy value to find. So this will be our base point in the linear approximation. By the way, I haven't said those words, I guess, but this is a linear approximation problem. We know that because they say find an approximation. So what do we do now? Well, you know that you need f prime of a in that process, so you better find f prime first. What is f prime? Okay, how do we compute the derivative of this function? This is the function 1/5 root. If you write that as x to the, it would not be 1/5, that is just the 5th root. Because you have also 1 over that, you need x to the minus that. This is the function that you have. You want the prime of that. That is a power rule. Okay, by power rule, you can find this derivative this way, minus 1/5 minus 1, which works out to be x to the minus 6/5 in the exponent. This is f prime of x. We know, given this derivative now, the one that we want is f prime of a. So where a was the number 32. So you need to find out this number, minus 1/5, 32 to the minus 6/5. Kind of a mess algebraically, but this is a number that's easy enough to write down. So you should try to compute this. I'm not going to finish the problem, as I said, but I just want to give you the ideas. What is L of x? Now the linear approximation is always like this. F of a plus f prime of a, x minus a. This is the process for finding a linear approximation. So a is 32, f of a we just computed, f prime of a is up here, whatever that is. So we know all those parameters. The final answer, the number that we're trying to find, that's f of 33. This is how the process works. We always say that it is approximately the linear approximation at 33. So now after writing this fully with the actual numbers in it, you plug in x equals 33 and into the, well, I guess the arrow goes the other way, 33 for x, and you're gonna find a number in here. So this number will be your answer to the linear approximation. Let me not finish this. Again, this is very similar to everything we've done in recitation, in lecture. But the problem is not over. The problem also asked, is this approximation smaller or larger than the actual value? So whatever this number is, maybe let's call that star. The question now is star larger or smaller than the actual number, the 1/5 root of 33? How do we determine that? We have to look at the graph of the function, 1/5 root of 32, or of x, sorry. That was the function. If this graph is a smile concave up, then the tangent line is below it, which means the approximation is smaller, because the approximation is always on the line. If the graph is a frown, which means concave down, then it's the opposite. The approximation would be larger. So we just have to determine if the graph of f is up or down. And instead of doing that by computing a second derivative, which is a thing that we can do, this one is simple enough that we can just reason thinking about the graph. Basically, what does the 5th root of a number look like? The graph of that? Well, that's basically essentially the same as the square root graph. Any kind of root would be just like this. This is the 5th root of x. looks similar to the square root. We only need to worry about positive numbers here. Now the actual function that we have is not this one, it's 1 over this one. So we have to take the reciprocal now, which means in another color, like in here where f is close to 0, the reciprocal would be very large. And in here where f is going towards infinity, not f, sorry, but the fifth root is going towards infinity, the reciprocal of a large number is going to be a small number going down to 0. So this graph looks like this. The green graph is f of x. And that's a smile. This is a graph that is concave up. F is concave up. So this implies, this is supposed to be an arrow here, not a smile. Well, this implies that the linear approximation, the tangent line, is below the graph. So the approximation, the number star, is less than the actual value. Star was the approximation, and this is the value. All right, so this is all for this problem. I have another linear approximation problem here that's more conceptual. I hope you're gonna find this one interesting. It's about physics. So in the theory of special relativity, Einstein's special relativity, if you have a particle of mass m and constant speed v, you can define the kinetic energy of that particle by this crazy formula here, where c is the speed of light. So E is just an expression. Now, what actually happens is that most matter particles will have a speed v much smaller than c. So this number here, v over c squared, is a really small number. So what this question is asking now is, write E as a function of the small number x v over c squared. Let's call that x. First of all, then, write E as a function of that, and then compute the linear approximation around x equals 0. And then finally write it in terms of v and c and not x. This is just the last step for us to see what happens. So anyway, writing E as a function of x is very simple. It is just replacing the thing that we just called x. X is v over c squared. That's right here. So I'm just replacing that by x, where m and c are just constants anyway. So this is E as a function of x. And as I said, x is a small number. So they're asking us to write E as a function of this small number x, and then do linear approximation around the number 0. They didn't call this A, they called it x. That's just a matter of wording, okay? What you have to think is that they are saying around. So this is the number that we usually call A, the point around which you're going to do the linear approximation. So our A is 0, and we want to do linear approx. Okay, for that, we are going to need to know E prime. So what is E prime of x? Well, let's do chain rule here once again, because you have functions of functions, 1 minus x, and then root. So you could say, for example, u is 1 minus x, and the function E in terms of u is mc squared over root u. As a function of u, once again, m and c are just constants. So E prime of x, dE dx, by the chain rule is dE du times du dx. Du dx is very easy to find. That is just minus 1, because u is 1 minus x. What is dE du? Well, mc squared is a constant, and E as a function of u is 1 over root u. So it is just u to the minus 1/2. That's what we want to find a derivative of in terms of u. So by the power rule, that becomes minus 1/2 times u to the minus 3/2. All right, so I'm going to multiply these two things together, minus 1 with this more complicated one. what you get is 1/2 mc squared u to the minus 3 halves, and then replace u with what it means in terms of x, which is up here, 1 minus x. To the minus 3 halves. All right. We needed e prime. Well, it is calculated here. Why did we need that? Well, once again, we're doing linear approximation of the e function around the number 0. So we need to find e of 0 and e prime of 0. Those are easy. What is e of 0? E is right here. Well, when you plug in x equals 0, you just get mc squared over 1. And what is e prime of 0? E prime is down here. When you put 0 for x, this is just going to be 1 raised to minus 3 halves. That is still 1. So that is a 1/2 mc squared. All right, so let's just try to remember these values, those three right here. The linear approximation, the function they asked us to compute as a function of x, that is f of a, f of 0, plus f prime of a, f prime of 0 in this case, times x minus 0. So of course x minus 0 is just x. This is the linear approximation as a function of x. We're actually almost done with the problem. The very last thing they asked after writing this is write in terms of v and c and not x. So now that we've done it in terms of x, just replace x with v over c squared again. That's what it meant in the problem. So here is v over c squared. And then you can see that if you simplify this, c squared with c squared goes away. You just have 1/2 times mv squared. This is the final answer for L of x. Well, if you ever take physics classes in relativity, you're going to do this calculation right here. This is an approximation for the kinetic energy of a particle in relativity. When its velocity v is small compared to c, which is usually the case, like this number x was small, which means the approximation is meaningful, right? And what is this formula saying? You may recognize this is called the static energy of a rest energy, I should say, of a particle, E equals mc squared. So every particle already has this first term of the energy, doesn't matter which speed it's going. And then the next term, you may recognize this formula. This is what is usually called kinetic energy, mass times velocity squared divided by 2. So this is why the expression is called kinetic energy. The real expression is this one. It's the function E. But when the velocity is small, this just becomes the rest energy plus the thing that we usually think about as kinetic energy. So it's a meaningful computation for physics. Moving on. This is now a remark that I wanted to include in the lecture, but I included it in here. There is nothing new here, but it's useful to remember. Some problems, they're actually going to ask us to estimate the difference. This is the keyword here, the difference in f of x when x changes by some amount, delta x. This is the number delta, the letter delta, the triangle. So in other words, the problems will, instead of asking you to find the linear approximation, they will say, estimate the number, the difference in the f values when x changes between x and x plus delta x. And you can call that number delta y. How do you do that? By using this formula. Now you can remember this formula if you want as a completely separate thing, but really this is all the same. It is given by linear approximation. How do we know that? Very quickly. So here is the number, delta y, that we're trying to estimate. Delta y equals f of x plus a small number minus f of the original x. According to linear approximation, f of x plus a very small number, imagine that you're doing linear approximation around the number x. So it looks like this. Instead of having a here, I have x. And now this x plus delta x is the number where we are trying to find the value of the function. So plug this into here and then subtract the f of x. So what do you get? This is going to be approximately, well, this right here, f prime times, and what is x plus delta x minus x? That is just delta x. So you can see that this is the formula that I have above. It comes from linear approximation. You don't have to think of this as a new formula. It's just a shorthand. It's just easier, quicker if you remember that. But let me do one example of a problem that does this. So in this problem, we have a cone. It may seem like a related rates problem because it has lots of words in it, but we know it's not because they say estimate the change. They're not saying calculate something, it's estimate. So it is linear approximation. So the problem is, basically we're gonna have a cone where one of the dimensions is changing, and we are talking about the total surface area of the cone, both the base and the lateral. So first of all, they're just gonna remind us that the lateral surface of a circular cone of base radius r and height h is given by this formula here, pi r root of r squared plus h squared. This is just a formula that you might not remember. I mean, I honestly did not remember this. We can calculate this, but anyway. So the area of this lateral surface in blue in my drawing, the surface around the cone, is given by this formula. Of course, the area of the base is pi r squared because that's the circle. All right, now the problem actually starts here. Suppose that you have a cone with a height that's fixed at 3. It's always 3. But the radius is initially equal to 4 and variable. It is going to change. The question is estimate the change in total surface area, including lateral and base, if the radius increases to 4.1. So you see, once again, this is linear approximation. You had a certain value of the function, and then it increased to a little bit larger, and they are saying to estimate. So first of all, we have to write down what is the function that we are estimating. We're trying to estimate a function of r, which is the total surface area of the cone. There is going to be the area of the base, pi r squared, plus the area of the lateral. That's the formula they gave us, pi r times root of r squared plus h squared is always 9. H is fixed, it's not gonna change. So the height of this cone is always 3. The height squared is always 9. This is the function, a of r. So estimate the change in total surface area when the radius increases to r equals 4.1. So the initial radius was 4. Initial. And then it becomes 4.1 final or later, whatever you want to call these guys. We're going to be thinking of this in terms of the formula that I gave previously, which is the variation in area is approximately the area prime at this initial value, maybe I call that one R0, times the variation in R. That's the formula in the previous slide. Just now, instead of calling them y and x, well, y is a, which is the function. X is r, which is the independent variable that's changing. But anyway, we need to know a prime of 4. Delta r, we already know. That's the easy one. Delta r is the difference in r values. Final minus initial, that's just 0.1. So no problem there. But what is a prime of 4? I'm going to compute that, and then I'm going to cut this part of the video where I computed. Okay, I computed the derivative here. I cut it from the video, this is not the main focus of today's recitation. You should be able to calculate this by using the appropriate derivative rules. For example, a chain rule for the square root, as well as a product rule between that guy and this r outside. It's all a derivative with respect to r. So this should be okay. Now we wanted a prime of 4. So plugging in r equals 4. This is 8 pi. Plus, when you have r equals 4 and in the square root here, it becomes root of 25. So that's 5. So 5 pi and then 16 pi over 5. So what is that? 13 pi, which is 65 over 5 plus 16. That is 81 pi over 5. A prime of 4 is 81 pi over 5. Now go back to your formula. In relating delta A to delta R, that's going to just give you 81 pi over 5 times delta R was 0.1 or 1 over 10. So the variation in area is approximately by this amount, 81 pi over 50. Now I'm going to go back to the problem just to point out what item B was. Now item B is asking you to express this change as a percentage in relation to the original area. When we say original area, we're thinking of what A was at the original R value, R equals 4. So A of 4. And we want the change, delta A, as a percentage. This is common in this type of problem. They might ask for this. What they are asking for is to express how much the change is compared to the original value of the area as a percentage, which is usually going to be a very small number in case you are just estimating things by linear approximation, because the change is always small. So this is what they're asking. We need to know A of 4. We never computed this one, actually. Remember, we only computed delta A, the approximation for delta A in this problem. So what is A of 4? Well, remember the formula for the A function was pi r squared plus pi times r squared plus 9, sorry. So if you find this, this is going to be a 36 pi. You have 16 from here, and then 4 times 5 from here, 20. So it's 36 pi. This is A of 4. Delta A we just found up here. You see that the pi's go away. So being careful here about how to write this. Yeah, the delta A, 81 pi over 50, divided by A of 4, 36 pi. So pi goes away, and you just have 81 over, well, 36 times 50. That would be 1,800. Yes. Well, this is the actual fraction. How do we find a percentage from here? Well, percentage is the same thing as multiply this by 100. So 8100 divided by 1800%, which is basically 81 over 18. You can simplify this a little if you want. Divide by 9. 9 over 2, 4.5%. This is just mental math here, but as you see, it's a small percentage, small variation, as you expect. So just be aware that problems will many times ask you not only to estimate the change, but then also find that as a percentage. And also be aware that what we have used in this particular problem here is this formulation of the linear approximation formula. The variation in the function compared to the variation in its variable is given by the derivative at the base value of the variable. So going back to the previous slide, it's basically this.